In the early hours, a powerful offshore earthquake struck near Japan's northeastern coast, prompting tsunami warnings and activating one of the world's most advanced seismic monitoring systems. This type of event is closely linked to subduction zone physics, where tectonic plates interact under immense pressure. Understanding how stress builds, how seismic waves travel, and how the ocean responds to sudden seafloor displacement helps explain why authorities act quickly and why coastal communities are urged to move immediately to safer ground. This breakdown focuses on the physics and mechanics behind the earthquake and the tsunami warnings that followed. What tectonic setting produces large earthquakes off northeastern Japan? The northeastern coast of Japan lies near the Japan Trench, where the Pacific Plate moves westward and dives beneath the Okhotsk Plate. This boundary is a subduction zone, meaning one plate is forced under another into the mantle. The plates do not slide smoothly. Instead, friction locks them together, allowing stress to accumulate slowly over time. The overriding plate bends and stores elastic energy while the subducting plate continues pushing forward. When the locked zone finally breaks, the plates slip suddenly, releasing the stored energy as a powerful earthquake. How stress builds and is released during the earthquake. As the plates remain locked, the upper plate is gradually dragged downward and compressed. This deformation stores elastic strain energy in the crust. When the stress exceeds the frictional strength of the fault, rupture occurs. The fault slips in seconds, and the bent crust rebounds toward its original position. This sudden motion is called elastic rebound. In offshore subduction earthquakes, part of the seafloor may lift upward while another part drops downward. This vertical displacement is the key mechanism that can generate tsunami waves. Why a magnitude 7.5 earthquake is considered powerful? Earthquake magnitude follows a logarithmic scale. Each increase represents a much larger release of energy rather than a simple step up. A magnitude 7.5 earthquake releases dramatically more energy than smaller, more frequent tremors. Compared to a moderate earthquake, the energy difference can be dozens of times greater. This large energy release increases the likelihood of significant ground shaking and raises the possibility of seafloor displacement capable of disturbing the ocean above. What seismic waves are generated when the fault ruptures? The rupture sends out different types of seismic waves. Primary waves travel fastest and move through the ground by compressing and expanding material. These waves arrive first and are often detected by early warning systems. Secondary waves follow more slowly and move the ground side to side or up and down. These waves usually produce stronger shaking. Because primary waves travel faster, detection systems can issue alerts before the more damaging shaking arrives, providing precious seconds for safety actions. How the earthquake generates a tsunami. When the seafloor shifts vertically, it pushes the entire column of water above it. This displacement creates long waves that spread outward across the ocean. Unlike wind-driven waves that affect only the surface, tsunami waves involve movement from the ocean floor to the surface. The energy travels across the sea in long wavelengths, often spanning hundreds of kilometers. In deep water, the wave height may remain small, making it difficult to detect visually even though enormous energy is moving through the ocean. Why tsunami waves grow near the coast. As tsunami waves approach shallower coastal waters, their speed decreases. The wavelength shortens while the energy remains largely conserved. This forces the wave height to increase, a process known as shoaling. The result is a dramatic rise in water level near the shore. A wave that appeared small offshore can grow into a powerful surge capable of flooding coastal areas. This is why warnings are issued even when offshore measurements seem modest. Why tsunami waves travel extremely fast in deep ocean water. Tsunami speed depends on ocean depth. In deep water, the wave can travel at speeds comparable to a jet aircraft. As depth decreases near land, the wave slows but increases in height. This relationship between depth and speed explains why distant coastlines may receive waves long after the earthquake while nearby coasts must react almost immediately. How authorities decide to issue tsunami warnings. Tsunami warnings are triggered by analyzing earthquake magnitude, depth, and fault motion. Models estimate how much the seafloor moved and how much water may have been displaced. If expected wave heights reach levels capable of producing strong currents or coastal flooding, authorities issue advisories or warnings. More serious predictions lead to stronger warnings and immediate evacuation guidance. These decisions are made quickly to protect coastal populations. Why Japan has strong early warning capabilities. Japan operates a dense network of seismic sensors and ocean monitoring systems. These instruments detect primary waves, measure ground motion, and estimate tsunami potential within seconds. Automated alerts can be transmitted to phones, transportation systems, and emergency services. This rapid response is designed to reduce risk even when warning time is short. How engineering in Japan reduces earthquake damage. Buildings in Japan are designed to absorb seismic energy rather than resist it rigidly. Techniques include base isolation systems that allow structures to move independently from ground motion, flexible steel frames that bend without collapsing, and dampers that dissipate energy. These systems are tuned to handle the long-period shaking typical of large subduction earthquakes. Why multiple tsunami waves are possible. A tsunami is not a single wave but a series of waves. The first arrival may not be the largest. Later waves can be stronger as reflections and interactions reshape the energy distribution. This is why officials emphasize staying away from the coast until all warnings are lifted. What makes offshore earthquakes particularly concerning? Offshore earthquakes are more likely to disturb the seafloor directly. Even moderate vertical displacement can move vast amounts of water. Because oceans transmit energy efficiently, waves can travel far from the source. Coastal regions near the epicenter face the greatest risk, but distant coastlines may also experience unusual currents and water level changes. What people should do during a tsunami warning. The safest action is to move immediately to higher ground or inland areas. Waiting to observe the sea is dangerous because waves can arrive quickly and without obvious signs. Following official instructions and staying informed through trusted agencies is essential. Harbors, rivers, and low coastal zones should be avoided until authorities confirm the danger has passed. How this event demonstrates the physics of tectonic forces. The earthquake illustrates how slowly moving tectonic plates can store enormous energy over time. The sudden release produces seismic waves, shifts the seafloor, and transfers energy into the ocean. The resulting tsunami depends on water depth, wave physics, and coastal geography. Understanding these mechanisms explains why warnings are issued rapidly and why evacuation decisions must be taken seriously. Finally, this event is a reminder of the powerful natural forces acting beneath the ocean floor. Subduction zone mechanics, elastic rebound, seismic wave propagation, and tsunami dynamics all combine within seconds. Early detection and engineering preparedness help reduce risk, but awareness and quick response remain critical. Stay safe and stay informed by following official updates and evacuation guidance. If you found this technical breakdown helpful, share the video, like it, and subscribe for more physics-based explanations of major global events.